So I'm going to talk today about some fairly low-level issues that I've been working on with regard to interpretation of functional connectivity. So mainly focusing on fMRI, but it's relevant to other areas as well. I have to really push hard. So I guess most people are probably fairly familiar with the definitions of functional connectivity if they've coming to this session. Briefly, these are methods that are simply trying to characterize correlations between neural assemblies or some sort of similarity between neural assemblies, and not trying to make inferences regarding the directness or indirectness of the relationship between the brain regions or the directedness and causal relationship between those regions. I mean, the benefits for using quite simple measures of functional connectivity is that you get you have a very flexible measure, this pairwise measure that you can characterize signals in a very flexible and in a variety of manners. It's also computationally efficient. We can do mapping of functional connectivity, and it's quite direct to the data, so we're quite easy to at least interpret in terms of what the data is telling us. But of course, it's quite a simple measure. It's not estimating any type of neurophysiological parameters, and it's going to be sensitive to a wide range of effects if we're looking at changes in functional connectivity. So it's quite difficult to interpret exactly whether what it's telling us about the underlying neural activity. Sort of the alternate approaches approaches of effective connectivity, where you have more sophisticated models trying to model a broader neural system. You'll be modeling the directedness of causal relationships between regions. You might be separating out direct and indirect connections. And in general, trying to obtain more neurophysiologically informative measures. And so they're obviously very major benefits, but it comes at the cost of you having to rely on quite large, highly parameterized models with a lot of assumptions. It can be difficult to, you need to trust the entire model even when you're interpreting individual parameters or connections. And it can be difficult. You need to be confident that your model is including all the sources of variance affecting the data. And often it's going to be difficult to include the many sources of variance, both neural and non-neural in such models. Ideally, we'd like to use functional connectivity to inform the design of effective connectivity models, and also to help us interpret effective connectivity modeling. However, this is really not done a lot. We sort of see these two parallel streams of functional and effective connectivity modeling. And I'd argue that partly this is due to some shortcomings in the way we characterize functional connectivity that makes it quite ambiguous, and it can't directly inform the effective connectivity models. So I'm going to talk a lot about correlation today and interpreting correlations, but a lot of this is going to be will be applicable to a variety of approaches to measuring similarity between time series. So unlike covariance, correlation is independent of the overall scaling of the signals. And ideally, this would would make this measure less sensitive to variability in the amplitude of the fluctuations we're measuring, say, across individuals, and be a nice, simple, direct measure of the similarity of signals. However, correlation has a problem if your signals are made of many components, as we do have in functional MRI. Because here the correlation is not going to be independent of the scaling of the separate subcomponents of the signals that we're comparing. So if, for example, noise levels, the simple measurement noise levels across two conditions vary, that's going to affect our correlation, despite its its apparent robustness to scaling. This factor that the scaling of individual signal components can affect correlation means that we can sort of conceive of quite a wide range of very diverse effects that might be affecting our functional connectivity measures. Traditionally, we might assume. The most traditional interpretation of functional connectivity might be that our brain activity is becoming more synchronized or less synchronized across conditions if we see a change in functional connectivity. And this is often taken as the sort of the final result that there's this change in functional connectivity between regions. But if we consider the scaling of these separate subcomponents of the signals, we can see quite distinct other factors that might be changing our functional connectivity. For example, there may be a change in the measurement noise levels, for example, head motion in a patient group that may be affecting our correlation in that group. Alternatively, it may be the amplitude of the signals that are shared across two regions that may be being modified relative to the background noise. And so while the core, for example, while the core signals and communication between the two regions remains the same, there's something about the fluctuations that makes them less variable, and therefore the correlations are lower. It's quite easy to consider quite distinct scenarios in functional imaging that corresponding to each of these scenarios. And so what we'd really like to be able to do is try to disambiguate these scenarios that have a more specific interpretation of our measurement of functional connectivity. One key additional piece of information we might use is the variance of the signals we're measuring. So in these scenarios I've described, for example, an increase in measurement noise level, it will often correspond to an increase in the variance of our signals due to the increased noise. It may be useful to use this information to disambiguate the potential sources of changes in functional connectivity. There's been quite a lot of studies that do characterize the variability or amplitude of resting state signals in fMRI. However, this line of research has been quite independent of, and there's not been a lot of studies that directly compare the amplitude and variance of changes to the functional connectivity changes and how they might be related. Recently, our group, we studied the amplitude variability in human connectome project subjects. And we found that indeed there were quite consistent networks showing correlated fluctuations in their amplitude across subjects. And that these networks and these fluctuations were associated with the changes in functional connectivity previously reported to be associated with an axis of behavioral variability across subjects. But a study that went more deeply into this was a study from Michael Cole and co-workers a few years ago that really looked at really conceptualized functional connectivity as changes in the shared and unshared components of signals. So you might conceive of the individual signals as having some shared component and then some other unshared component, which could either be noise or simply neural activity that's not not common across the two regions. And the conceptualization of these changes, the changes in amplitude in these separate components might be driving functional connectivity changes, suggested that covariance and correlation may have different relationships. In some cases, covariance and correlation may increase when it's a shared component increasing in amplitude. In other times, it may be the opposite when it's a noise component. And so Cole looked at across a series of studies to see if indeed you do find these different scenarios where in some cases correlation and covariance went along with each other, and other cases they showed differing effects, suggesting that the underlying functional conductivity changes might be due to different sources, like I've described. And they certainly found quite substantial associations between the two, suggesting that quite a large amount of functional conductivity changes seem to be driven by changes in the amplitude of either shared or unshared components. Questions that our group has been asking is on a similar line of attack, but we were wondering if you can get an analytic technique to see if we can directly test if a change in functional conductivity might be potentially due to these simple changes in component amplitudes, and so test whether that may be the case. That is, are the observed changes in variance adequate? Do we observe changes in variance, and are they adequate to explain the observed change in functional conductivity? This involves designing having to define a model of exactly what these signal component amplitude changes might be. So we conceptualize it similarly to Michael Cole, where we have two conditions, A and B, and we see that the second condition as containing the same stochastic signals as the first condition, but then some addition of some additional stochastic signal, maybe additional increase in a particular component. And we can put constraints on the nature of that additional signal to correspond to certain types of signal amplitude changes. The simplest example is if this new signal is uncorrelated with all the existing signal. So that may be an increase in uncorrelated measurement noise in a second condition. In this scenario, with that constraint, we can actually estimate, given the initial correlation and the changes in variance we see, what we'd expect the correlation in the second condition between the two regions to be exactly. It would be basically the initial correlation scaled by the ratio of the changes in variance. So we can turn that into a test. Does the observed correlation correspond to what we might expect to see given an increase in measurement noise? And we can take into account observational uncertainty there. We've defined a more general class of called additive signal change, which tries to encompass a broader range of changes in the scaling of signals. So that maybe there may be a common increase in a common shared signal or some mixture of changes. This is defined quite simply that the additional signal here can be any type of signal, but as long as it is not negatively correlated with the initial signal. That particular constraint of this increase, of this change between two conditions, ensures that this class of signal change always produces a change in variance. So you always see variance changes if there's an additive signal change. So what we can do, we can define, using optimization techniques, we can define the range of correlations in the second condition that can be explained by this class of additive change, where the change is due to increases in the amplitude of signals. And so that means we can classify changes in functional conductivity according to whether they potentially can be explained by the observed changes in variance we see that go along with them. And we also define these subclasses, like the purely uncorrelated signal, which is a subclass of the broad additive class. This means we can classify functional conductivity and determine whether or not they may be due to the changes in amplitude. So we've tested this in a range of empirical data over the last 6 months or so, and indeed we do find, by and large, that changes in functional conductivity can be explained by the corresponding changes in variability in particular regions going along with it. In this case, we had a visual. We contrasted a movie watching to a rest period, and we see in the visual networks increased in the amplitude of their fluctuations, and that increased correlations between the visual nodes, as you'd expect if there was this common driving signal producing the change in functional conductivity, and also decorrelated the visual networks from other brain regions. There were some small number of regions that couldn't be explained by this, or a small number of connections that couldn't be explained by these amplitude changes, however. Similarly, we found similar results in the functional connectome project, where these amplitude changes could be predicted the correlation changes. Just very briefly, I'll talk about this type of analysis has close relationship to certain types of effective connectivity analysis, in particular structural equation modeling, where directionality of relationships between regions is determined based on the variance-covariance relationship between them. So what this additive signal analysis can do is allow us to interpret the types of signal dynamics that are driving our effective connectivity models. And indeed, DCM has a slightly more sophisticated model, but it still is driven by similar signal features. So just to summarize, apparently the autocorrect assumes that functional connectivity is sometimes fictional connectivity, according to Jack Gallant. I don't think that's exactly true, but I think functional connectivity measures need to be interpreted very carefully, and I think many of them will be corresponding to these changes in the amplitude of the activity in brain regions, rather than pure synchronization or desynchronization of brain regions. Reporting covariances rather than simply the correlations makes it a lot more disambiguates the functional connectivity measures and allows us to potentially interpret effective connectivity models or drive them, and to potentially allow functional connectivity analysis to be more useful in meta-analysis. We're looking at further approaches of these sort of methods. Things like psychophysiological interactions have the same dynamics associated with them. You can do similar sort of models with dynamic functional connectivity, and also analyses in the frequency domain have also similar properties to this. So I think that's all now. I thank my co-authors Tamar Macon, Mark Ulrich, Steve Smith, and the analysis group at FinRib. Thank you.
Great.